300,000 kilometers per second. That's the limit, they told us. The law that governs the entire universe, unshakable as gravity itself. But what if it's not? Right now, somewhere in laboratories with long corridors and humming fluorescent lights that flicker just slightly when you're not looking, a group of physicists is quietly dismantling everything we thought we knew about traveling through space. They're not just approaching light speed, they've found a way to surpass it, 10 times over. And this changes everything, though most people don't know it yet. Imagine this for a moment. Really, picture it. Alpha Centauri, the nearest star system to our own, sits 4 light-years away from Earth. 4 years traveling at the speed of light, which sounds almost reasonable until you realize we can't even get close to that speed. With our current technology, the best rockets we have, the ones that took us to the moon and sent probes past Pluto, it would take roughly 70,000 years to reach Alpha Centauri. 70,000 years. That's longer than all of recorded human history, longer than we've had agriculture, cities, writing, longer than we've been anything resembling civilization. But if what these scientists are saying holds true, if the mathematics they're verifying right now in particle accelerators and gravitational wave detectors actually works in practice, we could be there in less than 6 months. 6 months to another star. Not science fiction, not a dream. Mathematics. Cold, hard equations that describe reality with brutal precision. Tonight, as you drift towards sleep, I want to walk you through 3 mysteries that surround this concept. 3 questions that keep physicists awake at night, staring at their ceiling, wondering if they've glimpsed something that will either save humanity or doom it. First, why Einstein might have been wrong, or rather, how his own equations, the ones that supposedly proved nothing can exceed light speed, actually contain a loophole he never noticed. A crack in the cosmic speed limit wide enough to fly a starship through. Second, what happens to the fabric of space-time itself when you try to cheat the universe's most fundamental law? Because space isn't empty nothingness, it's a thing, something that can bend and stretch and tear, and what we're proposing to do to it, well, it's unprecedented. And third, the darkest question of all, why some of the smartest people on Earth are terrified of this technology. Why they whisper in hallways after conferences that maybe, just maybe, we shouldn't build this. That maybe the silence of the cosmos, the strange, eerie absence of alien civilizations, is trying to tell us something. By the time you fall asleep, you'll understand something that only a handful of humans currently grasp. Something about the true nature of reality, about the fabric that holds existence together, about how fragile and strange our universe really is. And maybe you'll never look at the night sky quite the same way again. Let's start with what you think you know. In 1905, a young patent clerk in Switzerland, a man whose job was to evaluate other people's inventions, mundane things like improved butter churns and electrical regulators, published a paper that turned physics inside out. Albert Einstein introduced the world to special relativity, and its central, brutal postulate was simple. Nothing can move faster than light in a vacuum. Not just difficult, not merely impractical, impossible. This wasn't some technical limitation we might overcome with better engineering, like breaking the sound barrier. This was a fundamental law of nature, as absolute as gravity, as unchangeable as the flow of time itself. Einstein explained why with elegant mathematics. When an object accelerates, its mass increases. The closer it gets to light speed, the heavier it becomes. At the speed of light, its mass would become infinite, which means you'd need infinite energy to keep accelerating it. Infinite energy. There isn't enough fuel in the entire universe to push even a single electron to light speed, let alone a spacecraft with human beings inside. This is a mathematical wall, impenetrable, absolute. For decades, this law was considered sacred, untouchable. Generations of physicists grew up understanding that interstellar travel would remain forever a dream, that we were trapped in our little solar system, that even the nearest stars would remain forever as unreachable lights in the night sky, romantic, beckoning, but eternally beyond our grasp. And here's where it gets interesting, because the official story is only half the truth. Einstein did prove that nothing can move through space faster than light, but he never said that space itself couldn't move faster. That's the critical distinction, and it's in this loophole that the greatest secret of modern physics hides. See, when we talk about the speed of light as a limit, we're talking about motion within space-time. Imagine a fish swimming in the ocean. The fish can swim at a certain maximum speed. It can't swim faster than its physiology allows. But what if the ocean itself is moving? What if a massive current is carrying the fish along with the water? Then, relative to the ocean floor, the fish could be moving much faster than its own maximum swimming speed. This is exactly what modern physicists are talking about. They're not trying to accelerate ships to light speed. That's impossible for precisely the reasons Einstein described. Instead, they're looking for ways to make space itself move. And when space moves, everything inside it moves along with it, including a spacecraft, including its crew, without violating a single law of physics. It sounds like magic, but it's pure mathematics. And the most astonishing thing is that this mathematics works. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was sitting at home watching a science fiction show. On screen, a starship entered warp drive and vanished instantly, streaking toward distant stars. Alcubierre was a serious scientist. He knew it was fiction, but instead of just laughing at the impossibility of it all, he asked himself a question. What if it were possible? Not the way they show it on TV, but somehow, some way that doesn't contradict physics. He started working with Einstein's equations, not special relativity this time, general relativity, the theory that describes how matter and energy curve space-time, the same theory that predicted black holes and gravitational waves, the one that's been verified thousands of times and never once been wrong. And after months of calculations, working late into the night with coffee going cold beside his papers, Alcubierre discovered something incredible. Einstein's equations permit the existence of what he called a warp bubble. Picture a ship surrounded by a special field, a bubble of warped space-time. In front of the ship, space contracts. Distances that were light years shrink to mere kilometers. Behind the ship, space expands. Kilometers stretch into light years. The ship sits in a flat region of space in the middle, a little island of calm where everything is normal and stable, but the bubble itself moves. It slides across the fabric of space-time like a surfer on a wave. And here's the key. Inside the bubble, the ship is essentially motionless. It's not accelerating. Its mass isn't increasing. It's just sitting there, stationary relative to its little patch of space. But that patch of space is racing through the universe. And Einstein's laws permit this because space itself isn't limited by the speed of light. It can expand and contract at any speed. We see proof of this every day. The universe is expanding. Distant galaxies are receding from us, and the most distant ones are receding faster than light. Not because the galaxies themselves are moving through space at that speed, because the space between us and those galaxies is expanding so rapidly that the total distance increases faster than light can cross it. This is an observed fact, not a theory, something we measure every day with telescopes. If space can expand faster than light naturally, why can't we make it do so artificially? Alcubierre published his work and the physics community exploded. Some called him a genius, others called him insane. But nobody could refute his mathematics. the equations were flawless. The Alcubierre metric, as it came to be known, was completely compatible with general relativity. Einstein, without knowing it, had left us a key to the stars. But there was a problem. Massive, seemingly insurmountable. To create a warp bubble required something that, as far as we knew, didn't exist in nature. Negative energy. Or, to be more precise, exotic matter with negative mass energy density. Normal matter attracts other matter gravitationally. Exotic matter would have to repel. Normal matter curves space one way, exotic matter would have to curve it the opposite way. And the amount of this exotic matter needed to create even a small bubble was simply astronomical. The first calculations showed it would require mass energy equivalent to the mass of Jupiter. No, not Jupiter. The mass equal to the entire visible universe. Absurd. Impossible. The end of the dream before it could even begin. Or so it seemed. Because science doesn't stand still, and in 2012, something happened that changed everything. Harold White, a physicist at NASA, revisited Alcubierre's calculations. He noticed that the original model assumed a bubble of a certain shape, spherical. But what if you changed the geometry? What if, instead of a sphere, you used a torus, a shape resembling a donut? White ran new calculations, and the results stunned the scientific community. With optimal geometry, the amount of exotic matter needed dropped by orders of magnitude. Not to the mass of the universe, not even to the mass of a star, to a mass equivalent to just a few hundred kilograms. Still, exotic matter that we don't know how to obtain, but no longer astronomical insanity. This was an engineering problem. Difficult, yes, but potentially solvable. White didn't stop at theory, though. He began experiments at a NASA laboratory called EagleWorks. He built an interferometer, a device capable of detecting the tiniest warps in space-time. If they could create even a microscopic warp under laboratory conditions, it would be proof of principle. It would show that the Alcubierre metric wasn't just mathematical abstraction, but physical possibility. The experimental results were ambiguous. Some measurements showed anomalies, strange fluctuations that shouldn't have been there, but scientists argued whether these were real effects or just noise in the equipment, electronic ghosts, artifacts of measurement. The work continues to this day, and every year the experiments become more precise, the instruments more sensitive. But the story doesn't end there, because while White worked on the practical side of warp drive, other physicists attacked the problem from a completely different direction. In 2021, Eric Lentz, a physicist from the University of Göttingen in Germany, published a paper that overturned everything we thought we understood about warp technology. He showed that you could create a warp bubble without exotic matter at all, without negative energy, using only ordinary positive energy organized in a specific way. It was like magic. Decades of exotic matter being considered an insurmountable obstacle, and suddenly someone shows it's not needed at all. How is this possible? Lentz used a concept he called a soliton. A soliton is a self-sustaining wave that maintains its shape while moving. Imagine a wave in a canal of water. Ordinary waves dissipate over time, lose energy, disappear. But a soliton is a special wave that remains stable indefinitely. Such waves exist in nature. We can create them artificially, and Lentz showed that an analogous structure could be created in space-time itself. His soliton wasn't just a mathematical construct, it was a working model, using only known physical phenomena. No exotica, no negative masses, just energy organized the right way. The catch? The amount of energy was still colossal. To accelerate a shuttle-sized ship to 10 times light speed would require energy equivalent to hundreds of solar masses. Less than the original Alcubierre model demanded, but still far beyond our capabilities. But reality gets even stranger, because just months after Lentz's publication, Another group of scientists released work that reduced energy requirements by several more orders of magnitude. Alexei Bobrik and Gianni Martir from the City University of New York showed that the classical bubble shape wasn't the only possibility. They developed an entire class of new geometries, some requiring significantly less energy. Their models still needed enormous power, but the trajectory of improvement was obvious. Every few years, someone found a new way to lower the requirements. Every few years, the impossible became slightly less impossible. And now we come to what's happening right now. To what made me start this story by saying scientists have found a way to travel 10 times faster than light. In 2024, a group of researchers led by physicists from Applied Physics, a private scientific organization specializing in advanced research, published results that even their colleagues haven't fully processed yet. They developed a mathematical model of what they called a passenger warp bubble. Unlike all previous concepts, this model accounted not just for the bubble's motion, but for conditions inside it. Because what's the point of a ship if the crew dies from tidal forces or radiation? Their model solved both problems simultaneously. It created stable, flat space inside the bubble where humans could live and work under normal conditions. And it required energy that could theoretically be obtained in the foreseeable future. Not tomorrow, not in 10 years, but perhaps within a few generations. And here's where it gets really interesting, because everything I've just told you is the official version. Published papers, open research, things you can find in scientific journals. But reality is much stranger and much darker, because there are things scientists don't like to talk about publicly, questions they prefer not to raise, discoveries that frighten them. Imagine for a moment that warp drive works, that we've learned to compress and stretch space at will. What does that actually mean? It means the ability to travel to the stars in days or weeks. But it also means something much more disturbing, because if you can manipulate space-time, you can do things with it that are terrifying to even contemplate. Some physicists have calculated that under certain conditions, a collapsing warp bubble could generate radiation comparable to a gamma-ray burst. A gamma-ray burst is the most powerful phenomenon in the universe. When a supermassive star dies, it releases so much energy it can sterilize planets thousands of light years away. One failed experiment with warp technology could destroy all life on Earth. Not a country, not a continent, the entire biosphere of the planet. Other scientists point to even stranger possibilities. If you can warp space, you could create closed, time-like curves, the scientific term for what science fiction calls time travel. And here begin paradoxes that make physicists' heads hurt. Could a warp drive ship return to the past? Could it arrive at a point before it departed? The equations say, theoretically, yes. The practical implications are impossible to even imagine. And there's one more question, the most frightening of all. If warp technology is possible, why don't we see evidence of it? The universe is nearly 14 billion years old. If intelligent civilizations exist, and by all calculations they should, why haven't they filled the galaxy with warp drive ships? Why is space so empty and quiet? Some think they know the answer, and it terrifies them to their core. Maybe warp technology is a filter. Maybe every sufficiently advanced civilization eventually discovers it, and maybe every civilization that discovers it destroys itself, either accidentally in a failed experiment or deliberately in a war where one side uses warp bombs against the other. Maybe that's why the universe is silent. Maybe we're standing on the threshold of a discovery that has already annihilated billions of civilizations before us. But this is just the beginning. Because what I'm about to tell you next is even stranger, even more frightening, and even more real. To understand how you might travel faster than light, you first need to understand what light is and what space is. because these two concepts are connected much more deeply than they appear. Light is an electromagnetic wave. It propagates through emptiness at 299,792 kilometers per second. Not 299,000, not 300,000. That exact number, precise to the meter. Physicists denote it with the letter C, and that letter is the most important in the entire universe. But why that speed exactly? Why not faster? Why not slower? The answer lies in the very structure of reality itself. Space-time isn't an empty stage where events happen. It's a physical object. It has properties. It can bend, stretch, oscillate. And it has a characteristic that physicists call the impedance of the vacuum, a resistance that emptiness offers to propagating waves.
It's from this impedance that the speed of light depends. Imagine a guitar string. The speed at which vibrations travel along the string depends on its tension and mass per unit length. Change the tension, change the wave speed. With space-time, it's exactly the same. The speed of light is determined by the intrinsic properties of space itself. And here's the key point. When you curve space, you change these properties. Not everywhere uniformly, locally. In a curved region of space, the laws of physics remain the same, but the geometry changes. Distances become different. Time flows differently. This isn't abstraction, it's experimentally confirmed fact. GPS satellites, the ones that make the navigator in your phone work, must account for the curvature of space-time around Earth. If they didn't, the error in determining coordinates would reach 10 kilometers per day. Earth's gravity, weak by cosmic standards, is already strong enough to noticeably affect the flow of time. Now scale this up. Imagine not Earth's weak gravitational field, but an artificially created warp millions of times more intense. Space ahead of the ship contracts so much that distances of light years collapse to kilometers. Space behind expands so much that kilometers stretch to light years. The ship in the middle remains in a flat region where nothing strange happens. To an external observer, the ship crosses the galaxy in mere days. For the ship's crew, the same amount of time passes. No time dilation, no twin paradox. Because the ship isn't moving through space, it's moving with space. But how do you create such a warp? Here begins the most difficult part. According to Einstein's equations, space-time curvature is created by matter and energy. The more mass or energy in a certain region, the stronger the curvature. This works for ordinary gravity. Planets, stars, black holes curve space around themselves. But to create a warp bubble, you need a special type of curvature. You need to compress space in one direction while simultaneously expanding it in another. Ordinary matter can't do this. It always attracts, always creates curvature of one sign. You need something that repels, something that creates curvature of the opposite sign. That's the exotic matter I mentioned. But here's what's interesting. Exotic matter isn't quite fiction. We observe traces of it in laboratories every day. The Casimir effect, one of the strangest phenomena in quantum physics, demonstrates the existence of negative energy under certain conditions. Imagine two perfectly flat metal plates positioned very close together, less than a micrometer apart. In the gap between them, quantum fluctuations of the vacuum are restricted. Only certain types of virtual particles can exist there. Outside the plates, there are no such restrictions. Result? Pressure outside turns out higher than pressure inside. The plates attract each other. This was predicted theoretically in 1948 by Dutch physicist Hendrik Casimir and confirmed experimentally in 1997 with incredible precision. The effect is real. Negative energy isn't fiction. The problem is scale. The Casimir effect creates pressure on the order of a Pascal. For warp drive, you need energies equivalent to stellar masses. The difference is roughly 40 orders of magnitude.
It's like if you needed to light a room and all you had was a single photon emitted by a firefly on the other side of the galaxy. But physicists don't lose hope, because the history of science is full of examples where seemingly insurmountable barriers turned out to be illusions. In the early 20th century, scientists believed atomic energy would remain forever inaccessible. The famous physicist Ernest Rutherford, who discovered the atomic nucleus, declared in 1933 that talk of practical use of atomic energy was complete nonsense. 12 years later, the first atomic bomb exploded. 23 years later, the first nuclear power plant went online. The history of fusion is similar. Decades of scientists trying to reproduce in laboratories the processes happening in the sun's core. Again and again, experiments failed. Critics said controlled fusion would always be 20 years away. Then, in 2022, for the first time in history, a fusion reactor produced more energy than was spent to initiate it. The breakthrough happened. The impossible became possible. Maybe warp drive is next in this chain of impossible things becoming real. Let's look at specific numbers. To accelerate a spacecraft with a mass of 100 tons to 10 times light speed, according to the latest models, would require energy on the order of 10 to the 53rd joules. For comparison, our entire sun over its entire existence, yes, 10 billion years, will produce approximately 10 to the 43rd joules. The difference is 10 orders of magnitude. We need the energy of 10 billion suns, each burning for 10 billion years. It sounds hopeless. But remember what I said about improvements. The original Alcubierre model required the mass of the entire visible universe. Harold White reduced it to Jupiter's mass. Eric Lentz showed you could do without exotic matter altogether. Each improvement lowered requirements by tens of orders of magnitude. If this trend continues, and there's no reason to think it won't, in a few decades we might reach energies that are actually accessible. Imagine a fusion reactor of the future. Not today's experimental installations, but industrial stations capable of producing terawatts of power for years. Imagine orbital solar power stations collecting the sun's energy directly, without atmospheric losses. Imagine antimatter production on scales that seem fantastic today. 100 years ago, a nuclear reactor seemed fantastic. 50 years ago, a personal computer. 30 years ago, the internet in your pocket. Technological progress accelerates. What seemed impossible to our grandfathers became routine for us. What seems impossible to us will become routine for our grandchildren. But energy isn't the only problem. There are others, no less serious. First, the horizon problem. When a ship is inside a warp bubble, it's cut off from the external universe by a causality barrier. Information cannot penetrate the bubble's boundary, neither in nor out. For the crew, this means complete blindness. They can't see where they're flying, can't receive signals, can't send messages. It's like falling into a black hole, only in a black hole's case, the event horizon is a point of no return beyond which even light can't escape. In a warp bubble's case, the horizon surrounds the ship from all sides. The crew is literally trapped inside their own piece of space-time. How do you pilot a ship under such conditions? How do you stop at the right point? How do you avoid collision with an asteroid or planet you can't see? Some physicists propose a solution. Plot the course beforehand, before entering warp. All calculations must be completed before departure. The ship will follow a predetermined trajectory like a bullet fired from a gun. No mid-course corrections, no maneuvering, just a blind jump from point A to point B. It's frightening. Imagine boarding a plane that will take off and land automatically with no pilot control during flight. If something goes wrong, if an obstacle appears in the path, if conditions change, nothing can be done. But maybe it's not as scary as it seems. Space is vast and empty. The probability of colliding with anything on the path between stars is vanishingly small. Distances between objects are so great that even with the unluckiest route,
The chance of hitting an asteroid measures in trillionths of a percent. Second problem, navigation. When you're moving 10 times faster than light, ordinary methods of determining coordinates don't work. Stars around you are redshifted into invisibility or compressed into a point behind you. Radio signals from beacons can't catch up to you. You're flying in absolute darkness, relying only on internal clocks and preliminary calculations. The slightest error in initial data accumulates with every second of flight. If you miscalculated speed by 1/1,000,000th of a percent, after a year of flight, you'll be thousands of kilometers from your target. And if you miscalculated direction, the miss could be light years. Navigation in warp space will require completely new technologies, perhaps gravitational sensors capable of sensing stellar masses through the bubble boundary. Perhaps quantum communication systems operating on principles we haven't discovered yet. Perhaps something completely unexpected. Third problem, Hawking radiation. Stephen Hawking showed that boundaries between regions with different space-time properties generate particles. This happens at black hole event horizons. It should happen at warp bubble boundaries. Calculations show that when moving at speeds significantly exceeding light speed, the bubble's front wall will generate an intense flux of high-energy particles. When the ship stops and the bubble collapses, all this energy will release instantaneously in the direction of motion. Picture this. You arrive at a distant star, you exit warp mode, and at that same moment, the planet ahead of you receives a radiation dose capable of destroying all life on its surface. You've reached your destination, but your ship has become a weapon of mass destruction. Some physicists consider this problem solvable. They propose warp exit schemes where energy dissipates gradually rather than being ejected in one pulse. Others aren't sure. We still don't understand too much, and here we come to an honest admission. Science doesn't have final answers to most questions about warp drive. We know the equations permit such a possibility. We know there are no fundamental prohibitions, but between theoretical possibility and practical realization lies an abyss. We don't know exactly how much energy will be required. Estimates vary by tens of orders of magnitude depending on the model. We don't know how to generate the necessary type of curvature. All existing concepts require materials or fields we don't know how to create. We don't know what side effects will arise. Each new paper reveals new potential problems. And most importantly, we haven't conducted a single experiment that directly confirms the possibility of warp drive. Everything remains at the level of theory, beautiful, mathematically rigorous, but unconfirmed theory. This doesn't mean the theory is wrong. General relativity was also unconfirmed theory 100 years ago. It took decades for technology to reach the level necessary to test it. Gravitational waves were predicted by Einstein in 1916. They were detected only in 2015, almost 100 years between theory and experiment. Maybe it will be the same with warp drive. Maybe our great-grandchildren will read about the first experimental confirmations and wonder why it took us so long. Or maybe they'll discover that the entire concept was a mistake, that somewhere in the mathematics hid an unaccounted variable that makes everything impossible. We don't know, and that's perhaps the most honest thing you can say. But lack of certainty doesn't stop researchers. Laboratories around the world continue working. Theorists search for new solutions to Einstein's equations. Experimenters refine instruments capable of detecting the tiniest warps in space-time. Engineers develop materials with extreme properties. And there's another aspect rarely discussed publicly. Military and intelligence agencies, organizations whose names don't appear in scientific journals. If warp technology is possible, it has obvious military applications. A ship capable of moving 10 times faster than light is impossible to intercept, impossible to track. It appears from nowhere and vanishes into nowhere. The perfect scout, the perfect weapon carrier, the perfect instrument for a strike against which there's no defense. There are unconfirmed reports of classified programs, laboratories working under secrecy,
budgets that don't go through normal funding channels. Whether this is true or not is impossible to verify, but it would be naive to assume such research is conducted only in open academic institutions. Space-time keeps its secrets, but humanity has never stopped before closed doors. We cracked the atom. We deciphered the genetic code. We reached the moon and sent probes beyond the solar system. Warp drive is the next frontier, the next impossible dream that perhaps awaits its time. But before we fly to the stars, we need to understand what we might encounter. Because the universe is not a quiet place. It's full of violence, destruction, and energies that exceed all human imagination. There's a place in the universe where space-time behaves almost like inside a theoretical warp bubble. This place is called the ergosphere of a rotating black hole. When a black hole spins, and most of them do, it drags surrounding space-time along with it. This phenomenon is called the lens-thirring effect, or frame dragging. Imagine a spoon stirring thick honey. Honey near the spoon starts rotating with it. Space near a rotating black hole behaves the same way. It literally gets dragged by the massive object. In the ergosphere, the region between the event horizon and the outer boundary of the black hole's influence, this rotation is so intense that remaining motionless is physically impossible. Even if you fire engines at full power and try to hover in place, space itself will carry you in the direction of the hole's rotation. You can be motionless relative to your patch of space, but your patch of space is moving. Sound familiar? That's exactly how warp drive works in theory. The ship is motionless relative to its bubble, but the bubble moves through the universe. The difference is that the ergosphere is a natural phenomenon, a side effect of extreme gravity. A warp bubble is an artificial construct, created purposefully. But the principle is the same. Space-time can be made to move, and everything inside moving space-time moves with it. Astrophysicists study black holes using X-ray telescopes, radio interferometers, and gravitational wave detectors. Each new observation adds data about how extremely curved space-time behaves. This data is invaluable for warp technology developers. It's as if nature itself set up experiments we're not yet capable of conducting in laboratories. On September 21st, 2023, the LIGO observatory detected a signal that puzzled scientists. Gravitational waves indicated the merger of two objects of unusual mass between a neutron star and a black hole in the so-called mass gap, where objects theoretically shouldn't exist. But what caught the attention of warp drive theorists was the strange structure of the signal. Part of the wave pattern resembled models predicted for artificial space-time warping. Nobody's claiming it was an alien warp drive. Most likely the explanation will be found within ordinary astrophysics. But the very fact that natural and artificial warps could look similar is important. It means someday we might use gravitational wave observatories to detect warp activity, our own or someone else's. The SETI Institute, the organization engaged in searching for extraterrestrial intelligence, has already included warp signatures in its list of potential signs of technological civilization, alongside radio signals, laser pulses, and traces of astro-engineering structures like Dyson spheres. Now they're looking for gravitational anomalies that might indicate warp drive ships, so far unsuccessfully. The cosmos remains silent on all frequencies, but absence of results is also a result. Either advanced civilizations are rare, or they don't use warp technologies, or they use them in ways we can't detect. Each of these options tells us something important about our place in the universe. There's another class of objects deserving attention in the context of warp physics: wormholes, or, if we use the formal term, Einstein-Rosen bridges. In 1935, Einstein and his colleague Nathan Rosen showed that general relativity equations permit the existence of tunnels through space-time. Two distant regions of the universe could be connected by a short passage.
Instead of flying millions of light years around, you could slip through directly in minutes. Wormholes and warp bubbles are different concepts, but they're based on the same principles. Both use space-time curvature. Both allow bypassing the light speed limit without directly violating it. Both require exotic forms of matter or energy. For a long time, it was believed that natural wormholes are unstable. Any attempt to pass through them would lead to instant collapse. But in recent years, models of stable wormholes have appeared, held open by quantum effects or special configurations of matter. If these models are correct, wormholes might exist somewhere in the universe naturally, or might be created artificially. The connection between wormholes and warp drive is deeper than it seems. Some physicists believe they're two sides of the same coin. Creating a stable warp bubble might be equivalent to creating a microscopic wormhole. Technology capable of one is probably capable of the other. Now let's look at the reverse side of these marvels, at what happens when energies of this scale spin out of control. The universe isn't a quiet garden with twinkling starlight. It's an arena of unceasing violence, explosions, collisions, cataclysms on a scale the human mind refuses to process. And the energies involved in these events are comparable to those required for warp drive. This isn't coincidence. It's a reminder of what forces we're proposing to play with. Let's start with gamma-ray bursts. I mentioned them earlier, but didn't explain what they actually are. A gamma-ray burst is a sudden release of gamma radiation, the highest energy type of electromagnetic waves. It lasts from a few milliseconds to several minutes. During that time, the source releases more energy than our sun will produce over its entire existence. In seconds, the energy of 10 billion years. These events are registered by satellites almost daily. Most occur in distant galaxies, billions of light years away. That's good news, because if a gamma-ray burst happened close enough, say within a few thousand light years, and if it were aimed at Earth, the consequences would be catastrophic. Gamma rays would destroy the atmospheric ozone layer. The planet's surface would be exposed to direct solar ultraviolet radiation. Photosynthesis in the oceans would cease, killing phytoplankton, the base of the marine food chain. Acid rain would poison soil and water. Mass extinction would sweep the entire biosphere. Some paleontologists link the Ordovician-Silurian extinction, the second largest in Earth's history, occurring about 450 million years ago, with a nearby gamma-ray burst. About 85% of marine species died. Life on Earth nearly ended. Now think about this in the context of warp drive. If uncontrolled exit from warp mode can generate radiation comparable to a gamma-ray burst, every voyage to the stars becomes a potential apocalypse. A ship's arrival at an inhabited planet could erase its biosphere before the crew could say hello. This isn't paranoia. It's a direct consequence of calculations published in peer-reviewed scientific journals. The problem is real, and it requires solution before we build the first warp ship. But gamma-ray bursts aren't the only example of cosmic violence. Look at neutron stars. A neutron star is the collapsed core of a massive star, all the mass of our sun compressed into a ball about 20 kilometers in diameter. Density is such that a teaspoon of neutron star matter weighs about 5 billion tons. Gravity at the surface is 300 billion times stronger than Earth's. At such density, space-time curves so much you can almost touch it. A light beam aimed horizontally above a neutron star's surface will bend and return to it within a few kilometers. Time flows noticeably slower than far from the star. Neutron stars rotate some hundreds of times per second. Picture an object the size of a city, spinning faster than helicopter blades, creating monstrous magnetic fields trillions of times stronger than Earth's. These magnetic fields, they're not just strong, they rewrite the laws of physics. In them, atoms stretch into needle-like structures. Electrons move only along field lines,
Ordinary matter behaves so strangely that our physics textbooks simply don't work there. And here's what matters. If we're going to warp space-time artificially, we need to generate conditions comparable to what exists near neutron stars. Not the same exactly, but on a similar scale of extremity. We need to create regions where the rules change, where space-time bends not gently like around Earth, but violently, drastically, impossibly. This isn't engineering anymore. It's cosmic architecture. We're proposing to build structures that mimic the most extreme objects in the universe: black holes, neutron stars, the cores of supernovae. And we're proposing to do this in a controlled way, safely, without destroying the solar system in the process. The hubris is breathtaking. But there's a deeper question here, one that goes beyond mere technical difficulty, a philosophical question that makes some physicists deeply uncomfortable. Should we do this at all? Because there's something strange about the universe, something that doesn't make sense, something that should disturb anyone who thinks about it for more than a few minutes.
The universe is 13.8 billion years old.
That's a long time. Stupidly long. Our sun is only 4.6 billion years old. There are stars that formed when the universe was a few 100 million years old. Plenty of time for civilizations to arise, develop technology, spread across the galaxy. The Milky Way contains somewhere between 100 and 400 billion stars. Even if only a tiny fraction have planets, even if only a tiny fraction of those planets develop life, even if only a tiny fraction of those develop intelligent life, the numbers are still enormous. There should be thousands, millions of civilizations in our galaxy alone. And if even one of them developed warp technology 1 million years ago, just one, just 1 million years, which is nothing on cosmic scales, they would have had time to colonize the entire galaxy. Not slowly, not gradually, explosively, exponentially. Send out ships to 1,000 star systems. Each ship builds a colony and constructs more ships. Those ships spread to more systems. Within a few thousand years, a blink cosmically, every star in the galaxy has been visited. This is called the von Neumann probe scenario, and the mathematics are inescapable. With self-replicating machines and warp drive, a single civilization could fill the galaxy in well under 1 million years. So where are they? The Fermi paradox, named after physicist Enrico Fermi, who first posed it formally. If aliens exist, and if interstellar travel is possible, where is everybody? The silence is deafening. We've scanned the skies for radio signals, nothing. We've looked for signs of massive engineering projects, nothing. We've examined thousands of star systems for anomalies, nothing. The galaxy appears utterly, completely, suspiciously empty of intelligence other than us. There are many proposed solutions to this paradox. Maybe intelligent life is incredibly rare. Maybe we're the first. Maybe we're looking in the wrong places or for the wrong signals. Maybe civilizations don't spread because they don't want to or don't need to. But there's another possibility, darker and more disturbing. Maybe civilizations do develop warp technology, and maybe it kills them. Not metaphorically, literally. Maybe there's something about warping space-time that's fundamentally dangerous. Maybe the first successful test of a warp drive inevitably results in catastrophe. An explosion, a space-time rupture, something that sterilizes the home planet. Or maybe it's more insidious. Maybe warp drives work perfectly but become weapons, so devastating that their mere existence guarantees civilizational suicide. Mutual assured destruction on a scale that makes nuclear weapons look like firecrackers. This is called the Great Filter Hypothesis. Somewhere between primitive life and galaxy-spanning civilization, there's a barrier. Most species don't pass it. And if warp technology is that barrier, we're about to test it. Some physicists lie awake thinking about this. They wonder if they're building the tool that will end humanity. They wonder if the Fermi paradox is trying to tell us something, that the silence itself is a warning. Stop. Don't build this. Turn back while you still can. But of course, we won't. We never do. The drive to explore, to expand, to push boundaries, it's coded into us as deeply as DNA. We climbed down from the trees knowing we might fall. We crossed oceans knowing we might drown. We split the atom knowing it might destroy us. And now we're going to warp space-time. Consequences be damned. Let me tell you about a man named Robert Forward. Died in 2002, not a household name, but among physicists interested in exotic propulsion, he's a legend. Forward was both a scientist and a science fiction writer, a rare combination. He worked on gravitational wave detection at Hughes Research Laboratories, pioneered techniques that would later be used in LIGO. He had the mathematics and the imagination, and he used both to explore what might be possible. In 1984, Forward published a paper proposing a practical interstellar spacecraft design. Not warp drive, this was before Alcubierre, but something equally audacious. A solar sail pushed by a massive laser array. His numbers were specific, detailed, terrifyingly ambitious. A Fresnel lens the size of Texas in orbit around the sun. A laser powered by solar energy delivering a petawatt beam, 1,000,000 billion watts, onto a sail kilometers across. Acceleration would be gentle but relentless. Within years, the sail would reach a significant fraction of light speed. Within decades, it would arrive at Alpha Centauri. The plan was crazy, but not impossible. Every component was based on known physics. The engineering was horrific, yes, but not forbidden by natural law. Forward understood something crucial. Interstellar travel doesn't require breaking physics. It requires breaking economic and engineering barriers, which is difficult but fundamentally different from impossible. His work inspired a generation. When the Breakthrough Starshot initiative was announced in 2016, a plan to send tiny probes to Alpha Centauri using laser-pushed light sails, they were building on Forward's decades-old concepts. But Forward also understood the dangers. In his science fiction novels, he explored the consequences of powerful propulsion technologies. He showed civilizations destroying themselves with tools meant for exploration. He understood that any engine capable of moving a ship between stars is also capable of destroying planets. Energy is energy. A ship's drive is a weapon. The line between exploration and extinction is thinner than we like to think. Now scale this up to warp drive, a technology that manipulates the fundamental fabric of reality itself. The potential for misuse isn't hypothetical, it's inevitable. Imagine a warp bomb. Instead of a ship inside the bubble, you place it empty. You aim it at a planet. You activate it remotely. The bubble appears, races across space faster than light, impacts the planet's surface. The bubble collapses, releasing its stored energy in one catastrophic pulse. The planet doesn't have time to react, doesn't have time to raise shields or launch countermeasures. One moment it's there, the next, its atmosphere is stripped, its crust melted, its biosphere sterilized. And there's no defense. You can't shoot down something traveling faster than light. You can't detect it approaching. It arrives before the light from its launch point. You can't run. Where would you go that it couldn't reach in minutes? Mutually assured destruction with nuclear weapons relied on warning time. You see the missiles launch, you have 30 minutes. You launch yours in response. Terrible, but stable. Neither side initiates because both die. With warp weapons, there's no warning time. No 30 minutes. No chance for second thoughts or diplomatic cables or hotline calls between capitals. Just instant annihilation from an attack you never saw coming. Game theory says this leads to preemptive strikes. If you suspect your enemy is developing warp technology, you must strike before they finish, because once they have it, you're defenseless. But they know you're thinking this, so they rush to strike first. And you know they know, so you rush faster. An arms race with no finish line, no stability, no equilibrium except mutual extinction.
Maybe that's what happened to the civilizations before us.
Maybe they built their warp drives. Maybe they used them for a brief period of exploration and wonder, and then maybe someone, somewhere, decided to weaponize them. And that was the end. Not gradually, not with time for monuments or last words, just sudden, final silence descending across the galaxy. We're walking the same path. We tell ourselves we'll be different, we'll be wise, we'll regulate the technology, control its use, prevent militarization. History suggests otherwise. Every technology humans have ever developed has been weaponized. Fire, agriculture, metallurgy, chemistry, aviation, nuclear fission, genetic engineering. Everything. There's no reason to believe warp technology would be different. Every reason to believe it would be worse. But let's step back from apocalyptic scenarios for a moment. Let's assume we're careful. Let's assume we develop warp drive responsibly, use it only for exploration, manage to avoid blowing ourselves up in the process. What happens next? First contact becomes not a distant dream, but an imminent possibility. If we can reach other star systems in weeks or months, we can visit hundreds of them within a human lifetime. And if life exists out there, even primitive life, even microbial, we'll find it. This changes everything about our place in the cosmos. We've spent all of human history wondering if we're alone. The question would finally be answered.
But finding life raises more questions than it answers.
Finding primitive life, bacteria, algae, simple organisms, tells us that life is common. That wherever conditions allow, chemistry self-organizes into biology. That the universe is teeming with life at all stages of development. Finding intelligent life, that's different. That tells us we're not special. That consciousness, technology, civilization, these aren't unique human attributes, but natural outcomes of evolution given enough time. And if we find ruins, dead civilizations, extinct species, artifacts of intelligence that no longer exists, that tells us something darker. That intelligence doesn't guarantee survival. That being smart enough to ask questions about the universe doesn't mean being smart enough to answer them correctly. Some scientists hope we find evidence of extinct civilizations, not because they're morbid, but because ruins would teach us something invaluable, what not to do. We could study their mistakes, understand what killed them, avoid their fate. Others pray we find nothing, that all those lifeless worlds remain empty of ruins, because if advanced civilizations routinely go extinct, it means the odds are overwhelmingly against us. It means we're probably next. But there's a third possibility, stranger and more unsettling than either of those. What if we find active civilizations, but they're all hiding? Think about it.
If the galaxy is full of intelligent species and they all have warp technology, why aren't they obvious? Why haven't they reached out? Why haven't they found us? Maybe because they've learned something we haven't. Maybe they know that visibility is dangerous, that announcing your presence to the cosmos is suicidal, that intelligent species survive by staying dark, staying quiet, avoiding attention. This is called the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his Remembrance of Earth's Past trilogy. The galaxy is like a dark forest at night. Every civilization is a hunter moving silently through the trees, making noise,
showing a light, revealing your position. These things get you killed. Because you can never be sure of another species' intentions. You can never trust that they're friendly. The safe assumption, the survivable assumption, is that everyone is hostile until proven otherwise, and by the time they've proven hostility, you're already dead. So civilizations stay hidden. They develop their technology quietly. They avoid drawing attention. They watch the galaxy nervously, looking for threats, ready to strike first if necessary. We, stumbling around with our radio broadcasts and our plans for warp drives, are the idiots shouting in the dark forest, drawing every predator straight to us. If this hypothesis is correct, developing warp technology might be the worst thing we could possibly do.
It would make us visible to every other civilization with similar capabilities. We'd go from insignificant to threatening, and threats get eliminated. Maybe that's the real great filter. Not developing the technology itself, but becoming visible because of it. Maybe civilizations routinely develop warp drives, and maybe, just as routinely, they're destroyed by older civilizations who see them as potential threats. It's a paranoid vision of the universe, but paranoia isn't irrational if there really are threats out there. And we have no way of knowing if there are or aren't until it's too late. This brings us to a critical question. If warp technology is so dangerous, should research be stopped? Should we deliberately not pursue it? Some say yes. They argue that the risks outweigh the benefits, that we should focus on making our own solar system livable, terraforming Mars, building habitats in the asteroid belt, constructing space colonies, before we even think about reaching other stars. They point out that we have millennia worth of expansion possible right here, without ever leaving the sun's influence. Thousands of asteroids to mine, moons to colonize, energy from the sun abundant enough to support a civilization of trillions. Why risk extinction for the sake of reaching other stars a few centuries earlier? Others disagree violently. They argue that not pursuing warp technology is itself dangerous. That remaining confined to one star system leaves us vulnerable to extinction from local events, a nearby supernova, a gamma ray burst, a rogue black hole passing through. They argue that survival of the species requires spreading beyond our solar system, that keeping all of humanity's eggs in one stellar basket is the real risk. And they argue something else, something harder to quantify but perhaps more important, that exploration is what makes us human, that turning away from the stars because of fear is surrendering our essential nature, that we might survive by staying home, but we wouldn't be us anymore. It's an old debate, and there's no easy answer. Both sides make valid points. Both sides have logic and evidence supporting their position. What's clear is that the decision will be made soon, not centuries from now, not by distant descendants, by us, within our lifetimes. Because the research is already happening. The papers are being published. The experiments are running. Knowledge, once gained, cannot be unlearned. And if warp technology is possible, someone will build it. If not America, then China. If not China, then Europe. If not governments, then private companies. If not Earth, then a Mars colony wanting independence. You can't stop technological development globally. You can only choose whether your civilization will be among the first to have it, or among the last. And being last in a technological arms race is historically a very bad position. So we're going to build it. The question isn't if, but when, and what we'll do with it once we have it. Let's talk specifics. Let's talk about what a real warp drive spacecraft might actually look like, because this isn't science fiction anymore. Engineers are drafting blueprints. Designers are solving problems. The ship that will first travel faster than light might be under construction before you're old.
Forget Star Trek. Forget sleek hulls and glowing nacelles. A real warp ship will look nothing like that. First, size. The optimal design, according to current models, is surprisingly small. Not a massive starship carrying thousands, a capsule. Cramped, just big enough for a handful of crew and essential systems. Why? Because the energy required scales with the mass you're moving. Every kilogram costs you orders of magnitude in power requirements, so you minimize mass religiously. Stripped down, Spartan, uncomfortable. The crew compartment will be tiny, maybe 3 meters across, like living in a van, not a house, for weeks or months of travel. No windows. The warp bubble makes them impossible anyway. No artificial gravity. Too complex, too heavy. Just restraints and handholds and cushioning to prevent injury during acceleration and deceleration. Life support will be minimal. Recycling systems for air and water. Pre-packaged food. Chemical toilets. Radiation shielding thick enough to protect against cosmic rays, but thin enough to keep mass down. It will be claustrophobic, uncomfortable, borderline unbearable. But survivable. That's what matters. The warp generator itself, that's the interesting part. Current designs envision something like a ring around the crew compartment, superconducting magnets possibly, or something more exotic we haven't invented yet. Materials that can handle the stresses involved without shattering or melting. The ring needs to generate a precise field configuration, not just strong, precise. The difference between compressing space in front and expanding it behind requires incredibly fine control. Off by a fraction of a percent, and the bubble either fails to form or forms asymmetrically, which probably tears the ship apart. Control systems will be entirely automated. No human can react fast enough to make adjustments during warp flight. Everything must be calculated beforehand and executed by computers running algorithms we're only beginning to develop. Power source. That's the unsolved problem. We don't have anything close to what's needed. Even with the most optimistic energy requirements from the latest models, we're talking about power outputs equivalent to entire planetary civilizations. Some propose antimatter. Matter-antimatter annihilation is the most efficient energy release possible. 100% conversion of mass to energy. A few kilograms of antimatter meeting a few kilograms of matter releases energy equivalent to dozens of nuclear bombs. But we can't produce antimatter in useful quantities. CERN, the world's most advanced particle physics lab, produces about 10 nanograms per year. We'd need tons. The gap between current capability and requirement is unbridgeable with any existing technology. Fusion might work. If we solve controlled fusion, and that's still a big if, we could potentially generate enough power. But we'd need fusion reactors orders of magnitude more advanced than anything currently on the drawing board. Not the experimental machines running for milliseconds. Industrial power plants running for months, producing terawatts continuously. Zero-point energy is sometimes mentioned. The idea that vacuum itself contains enormous energy we might learn to extract. This is highly speculative. Most physicists are skeptical, but the theoretical basis exists. The Casimir effect proves vacuum energy is real. The question is whether it can be extracted at useful scales. Or maybe something we haven't thought of yet. Some new physics discovered in the next decades that provides an energy source we currently can't imagine. History is full of examples. Radioactivity was unknown before 1896, and within 50 years we'd built reactors and bombs. Maybe we're 50 years from a similar revolution. The first warp ship won't be comfortable, won't be safe, at least not by current standards, won't have backup systems or redundancy or escape pods. It will be a desperate, minimal machine barely capable of its mission. The crew that flies it will be volunteers, fully aware of the risks. Probably military pilots or test astronauts, people trained to accept danger as part of the job. They'll know there's a decent chance the ship will fail, that they'll die in the attempt. They'll go anyway.
Because that's what explorers do. Because someone has to be first. Because the drive to see what's beyond the horizon is stronger than the fear of death. History remembers names like Gagarin, Armstrong, Aldrin, the first man in space, the first men on the moon. History will remember whoever first travels faster than light, and that memory will last as long as human civilization exists. The mission profile will be carefully chosen, not Alpha Centauri for the first flight, too far, too ambitious. Probably something closer, Barnard's star at 6 light years, or one of the brown dwarfs recently discovered within a few light years of Earth. An object close enough that if something goes wrong, if the ship needs rescue, there's at least a theoretical possibility of reaching it. The flight will be monitored from Earth. Gravitational wave detectors tracking the ship's warp signature, radio telescopes listening for any signals that might penetrate the bubble, mathematical models running constantly, comparing predictions to observations, updating estimates of success probability. And then, after weeks or months, the ship will arrive. The bubble will collapse. Either the crew will send a signal confirming survival, or they won't. If they don't, there will be a funeral. Speeches about bravery and sacrifice, their names added to monuments, and then plans for a second attempt, incorporating lessons learned from the first failure. If they do, if that signal comes through, weak and distorted but unmistakable, everything changes. The first message from another star system won't be from aliens. It will be from us, sent to ourselves. Proof that the barrier has been broken, that the light speed limit was never really a limit at all, that the galaxy is open to us. And then the flood begins. More ships, better ships, cheaper ships as the technology matures. Within a generation, dozens of star systems visited. Within a century, hundreds. Within a millennium, if we survive that long, we'll have colonies scattered across the Orion arm of the galaxy. Humanity will become a multi-star species. Our extinction will require more than a single disaster. We'll have backups, redundancy, civilizational insurance written across light years. Unless, of course, we destroy ourselves first. Unless the dark forest is real, and something out there is waiting for us to make ourselves visible. Unless warp technology proves to be the filter that no civilization passes. But we won't know until we try. And we're going to try. That much is certain. Let me tell you about something strange that happened in 2012, something most people never heard about, but that sent ripples through the physics community. A laboratory in Germany was conducting experiments with high-powered lasers, trying to generate exotic particle effects. They were blasting tiny targets with focused energy, pulses lasting mere femtoseconds, but carrying enormous power. During one test run, their instruments detected an anomaly, a brief, inexplicable distortion in their measurement equipment. Gravitational sensors registered a spike, just for a nanosecond, but unmistakable. The spike was consistent with a localized warping of space-time, tiny, microscopic, but there. The team ran the experiment again and again. Sometimes they got the same result, sometimes nothing. The effect was unrepeatable, or rather, only partially repeatable. They couldn't control it. They published their results cautiously. No grand claims, just anomalous readings requiring further investigation. The paper got lost in the flood of scientific literature. Few people paid attention, but some did. Other labs tried to replicate the experiment. Most failed. A few claimed they saw similar effects. The data was always noisy, always ambiguous, always at the edge of detectability. Was it real? Was it instrumental error? Was it the first glimpse of space-time manipulation under laboratory conditions? Or was it just wishful thinking and confirmation bias? Nobody knows for certain. The experiments continue. The instruments get more sensitive. The theoretical understanding deepens. And every year, a few more papers appear in obscure journals, describing strange effects that might be evidence that warping space-time isn't just theoretical. I mention this because it highlights something important. We might be closer to breakthrough than official statements suggest. The line between impossible and we just did it is sometimes crossed quietly, in basements and labs, before anyone realizes what's happened. The first nuclear chain reaction was achieved in a squash court under a stadium at the University of Chicago. Witnesses said Enrico Fermi was so calm about it, so matter-of-fact, that you'd think he was conducting a routine chemistry demonstration rather than proving humans could unleash the power of stars. The first practical laser was built in 1960 by Theodore Maiman in a corporate research lab using a ruby crystal and photography flash lamps. Equipment so simple, it seems absurd that it took until the 1960s to invent. The first transistor was built at Bell Labs in 1947, and the engineers involved had no idea they'd just created the foundation for all modern computing. They thought they'd made a slightly improved version of existing amplifier technology. Revolutions don't announce themselves. They creep up quietly. They happen in places nobody's watching, and by the time the world realizes something fundamental has changed, it's too late to prevent it. Maybe warp drive will be the same. Maybe it's already happening in some classified lab or private research facility. Maybe the breakthrough occurred years ago and is being kept secret for strategic reasons. Or maybe we're still decades away. Maybe the problems are harder than optimistic researchers claim. Maybe every claimed detection of space-time warping is just noise and error. The honest truth is we don't know, and that uncertainty is perhaps the most fascinating part. We're living through a moment where something revolutionary might be just around the corner, or might remain forever out of reach. Schrödinger's breakthrough, simultaneously achieved and impossible until observation collapses the uncertainty. Let's talk about the economics for a moment, because money drives technology as much as physics does. Building the first warp drive will cost trillions, not billions, trillions. The R&D alone, decades of research, experimental facilities, prototype systems, will dwarf the cost of the Apollo program or the Manhattan Project. No single nation can afford it. Not anymore. The US spent roughly $25 billion on Apollo, about $150 billion in today's money. That was manageable because the economy was strong and the political will existed. A warp drive program would cost perhaps 100 times that, multiple trillions over multiple decades. It requires international cooperation on a scale never attempted. Or it requires private funding from sources we can barely imagine. Some think corporations will do it, that companies like SpaceX or Blue Origin will evolve into entities capable of funding such research. That the profit motive, exclusive access to interstellar space, monopoly on whatever resources or discoveries lie among other stars, will drive investment. Others think it will be governments, but only after some crisis makes it necessary. After an asteroid near miss that makes humanity realize we need off-planet backup. After first contact with alien life creates a space race more intense than the Cold War competition. Still others think it won't happen at all, that the costs are simply too high, the time frames too long, the risks too great. There will remain a single planet species indefinitely, expanding through our solar system, but never beyond it. I don't know which future we're heading toward, but I know this: someone, somewhere, is working on it right now. Someone is writing equations, running simulations, building experimental apparatus. Someone is convinced it's possible and is dedicating their career to proving it. And if history teaches us anything, it's that determined, obsessive humans eventually succeed at things everyone else said were impossible. The Wright brothers were bicycle mechanics. Their competitors had advanced degrees and wealthy patrons. Everyone knew heavier-than-air flight was impossible, or at least decades away. 4 years after Kitty Hawk, airplanes were flying over Europe. 20 years later, Lindbergh crossed the Atlantic. 40 years later, jets. 60 years later, supersonic passenger travel. From impossible to routine in a human lifetime. Maybe warp drive follows the same arc. First flight in 2080, regular traffic to nearby stars by 2150, an interstellar civilization by 2300. Or maybe it doesn't. Maybe this is the one barrier we never cross. Maybe the universe really does forbid it, and all our mathematics and cleverness can't overcome fundamental physical limits. Time will tell. But I think, and this is just my opinion, not physics, I think we'll do it. I think the drive to explore is too strong. I think the theoretical foundations are too solid. I think we've come too far to turn back now. In 50 years, or 100, humans will travel to other stars. They'll walk on planets orbiting alien suns. They'll send back images and data from worlds we currently can only dream about. And they'll do it not by going through space, but by carrying space with them. Not by traveling faster than light, but by redefining what travel means. Einstein showed us that space and time aren't fixed stage where events happen. They're dynamic, flexible, malleable. We're only now beginning to understand what that really means, what it allows. What becomes possible when you stop treating the universe as given and start treating it as something you can modify. Warp drive is our first attempt to become engineers of space-time itself, not just users, not just observers, but shapers, builders, architects of reality's fundamental structure. It's terrifying and exhilarating and entirely human. Of course we're going to do this. We've never encountered a frontier we didn't cross, a boundary we didn't push, a limit we didn't test. The speed of light was never going to stop us. It was only ever going to slow us down slightly while we figured out the workaround. And now we have. Mathematically, at least. The equations are written, the theories are published, the path forward is visible, even if it's difficult and dangerous and strewn with obstacles. What happens next depends on us, on our choices, on our wisdom, or lack thereof, on whether we're smart enough to use this incredible tool responsibly, or whether we're about to demonstrate why the galaxy is so quiet. Either way, we're about to find out. The experiment is running. Humanity is the test subject. And the results will be visible across the cosmos in ways we're only beginning to understand. 300,000 kilometers per second. That was the limit. Until it wasn't. Welcome to the future. It's faster than you thought.